This video is about integrals of powers of sine and cosine. As always, begin by reading through the textbook and taking some careful notes, but now consider the following highlights for this topic. We're going to recall several things, and many of these will go back to some hopefully familiar looking formulas or identities. From trigonometry, we need many things. For example, we'll recall the Pythagorean identity. And any algebraic equivalent. So the basic Pythagorean identity could be described as sine squared x, or sometimes you could use theta instead of x, right? You might see it a couple different ways, but it amounts to the same thing. So let's say in this form we have sine squared x plus cosine squared x equals 1. This is a very basic trigonometric identity from any introductory trigonometry class that you've probably seen before. Secondly, though, as you'll recall, you can use any other algebraic equivalent to this. So, for example, if you take this original Pythagorean identity we just recalled and you divide every term by sine squared of x or cosine squared of x, then you get some alternate forms of it that are ultimately equivalent and just as useful. For example, you could also say that secant squared of x equals 1 plus tangent squared of x. Or thirdly, cosecant squared of x equals 1 plus cotangent squared of x. Again, those are all just algebraically equivalent to the first one, simply by doing some manipulation on the terms. That's fairly basic, but we could use any of those. Sometimes I say if you have trouble memorizing all of those, just remember the first one and then practice getting the other two from it, doing those basic algebraic steps. Secondly, let's also recall that we have double or half angle identities. So, for example, the formula for sine would be the following. Sine of 2x, there's the double angle, equals 2 sine x cosine x. Again, that should sound and look familiar if you've been in trigonometry at any point somewhat recently. For cosine, there are a few options. So cosine 2x, there's the double angle, could equal one of three things, or any of these three things. The first one listed here is cosine squared x minus sine squared x, or it could also be equal to 1 minus 2 sine squared x, or thirdly, it could be equal to 2 cosine squared x minus 1. And any of those will work as a value for the double angle for cosine, that is cosine of 2x in this case. Or thirdly, you may recall some power-reducing formulas. These are also related to what would be known as half-angle identities. If you go back and look through some trigonometry material, I think you'll find these closely related. The power-reducing formulas that will be useful to us are as follows. Sine squared x is equal to 1/2 times the quantity 1 minus cosine of 2x. Now, sometimes you might see that written a little bit differently, like some textbooks write it with the 1 minus cosine of 2x all over 2 instead of putting the 1/2 out front. Of course, that's equivalent, but that will become useful. Or secondly, cosine squared of x is equal to 1/2 times the quantity 1 plus cosine 2x. And so again, sometimes these are referred to as power-reducing formulas because they go from, for example, a squared sine down to a non-squared cosine, or a squared cosine down to a non-squared cosine. So you're reducing the powers of those trig functions. Let's also recall some basic trigonometric derivatives. Of course, these will probably already be memorized by you at this point. If not, brush up on them. They should be memorized. For example, the derivative with respect to x of sine of x is equal to cosine of x. Or secondly, the derivative with respect to x of cosine of x is equal to negative sine of x. Again, those should be familiar, but make sure they're nice and fresh and memorized for us, what we're going to be needing here. Or next, let's recall, or I guess not recall, but now introduce a general strategy for integrals involving powers of sine and cosine, which is what we're doing in this topic. Now, these strategies are just kind of bullet points that we'll be using in no particular order. We want to, of course, do some examples shortly that help us use and practice them, but they are as follows. We want to decide which single factor of sine or cosine to leave behind for substitution. Now, there's some vague language in this that I think will come clear when we do some examples, but once you see those examples, I think this language will make more sense and why it is actually helpful. Or secondly, we're going to use identities and or substitutions to create a doable integrand. Again, doable is a pretty vague term, but you will see how we're kind of using what we have above. And for instance, substitution methods we already know for integration to put something more doable in our picture from the problem we have. Again, examples will help, so let's go there next. Our first example reads as follows. We want to evaluate the definite integral from 0 to pi over 2 of cosine to the 9th of x times sine to the 5th of x dx. Okay, so we have a definite integral, and certainly there are some trig functions lurking within it. We have cosine to the 9th of x and sine to the 5th of x as already read through. Now, I want to point out something we're going to want to start to catch or notice. Notice how these powers of sine and cosine are both odd, which means if we want to break these apart to, quote, leave one behind, as I said above, there might actually be a couple ways to do it. I'm going to demonstrate it by picking on the sine function, but you could very well do a problem sometimes by picking on the cosine in this case, just as in the same way. So here's what I mean. Since we look at the power of sine, in this case it's sine to the 5th, since that is an odd power of sine, what we're going to do is consider that to have an extra power that we can break off and leave behind. So I'm going to put this as just kind of a little side note. We're going to leave one extra, quote, behind. Now, that's just some general or vague terminology. I think it'll make sense here when I go through it. Let's rewrite this entire integral as it was given from 0 to pi over 2. Those bounds are just staying as they are for now. Then we had cosine to the 9th x. I'm just copying that down. And as I said, you might be able to pick on cosine just as well as sine in this one. I'm going to pick on sine, though, as mentioned. So I'm going to say now, instead of sine to the 5th, remember I said it's odd, so let's leave one extra behind. Well, what do I mean by that? I mean, let's rewrite that as sine to the 4th x times sine x. So notice I'm still accounting for all 5 of those powers of sine of x. But that one extra is what I'm kind of breaking off. So now I wrote it as sine to the 4th times sine. And you may say, well, why are we doing that, right? Well, it'll become clear soon. But this is just an example of how you can use this method of kind of splitting apart these powers. Now, why might this be useful? Let's keep going. So we want to go from 0 to pi over 2. That's what we're working on. Again, I'm going to leave the cosine alone for now. Cosine to the 9th of x. And then instead of writing sine to the 4th of x, which is part of what I kind of broke apart, I'm going to rewrite that in a more useful term, because also, recall from above our Pythagorean identity, we know that sine squared x plus cosine squared of x equals 1, which means I can do some simple algebra if I have a sine squared, really, or a cosine squared, but I said we're picking on sine for this one, so I'm going to stick with that and say this. Sine squared, if I were to solve for it in the Pythagorean identity, I could say that sine squared of x is equal to 1 minus cosine squared of x. Now, that's nothing fancy. If you're used to trigonometry, you're just getting one of those terms by itself, and we're going to use that now by saying instead of, instead of sine to the 4th of x, which is what we had as part of our integrand, and once we split off that extra sine, we're going to rewrite that as sine squared of x squared. All right, now I'm going to try to color coordinate some things here so this looks hopefully visually followable. All right, so we wrote sine to the 4th x as sine squared of x squared. Now, let's not forget what else we still have. There's this extra sine of x and then our dx. Those have to remain where they were because we're not changing the entire problem. We're just rewriting it in a more convenient way. Now, why would we rewrite sine to the 4th of x as sine squared of x squared? Well, of course, they're equivalent. And we know what sine squared is equal to, which is 1 minus cosine squared of x. So let me rearrange a little bit and then make some space to start working with this a little bit more algebraically. If we now rewrite what we have as the integral from 0 to pi over 2, nothing different there, times cosine to the 9th of x, as we had, times, instead of sine squared squared, I'm going to rewrite that as 1 minus cosine squared of x squared. So what we're doing is simply a substitution here algebraically. We are taking what we had previously, sine squared, and the fact that we know sine squared is equal to 1 minus cosine squared, and simply replacing one with the other. Now, why would we do this? Well, I think it'll become evident shortly, but for now, that's all we're doing is that replacement. And then, of course, we still have our sine x dx at the end. Okay, now, why would we do this, right? Well, if algebraically at this point we do some simplification by expanding the 1 minus cosine squared, and then combining these terms, you're going to find that a substitution is now possible. Because if I let's see, I'm going to do this over to this side. Let's let now u, I'm going to use the letter u for a substitution, equal cosine of x. Okay, now why would we do that? Well, we have cosines in our first two factors, and that was partially because there was originally a cosine in our integrand, but then also partially because we replaced the sine squared with a 1 minus cosine that also brought cosines in the picture. So it was actually a helpful step to have only cosines in the majority of this integrand, and then a sine x dx left behind, quote, at the end. Why? Because if I let u equal cosine of x and use a basic substitution, that means du equals, well, the derivative of cosine would be negative sine x dx. Again, this is just doing a basic u sub derivative here, which means I can replace sine x dx. Of course, I'm off by a constant, but that's easily fixable. So why would we do that? Well, let's figure out. If I then take another step, call this the integral from 0 to, well, actually, be careful. Let's get our new bounds now that we've used a substitution, right? If I let u equal to cosine of x, that means my new bound, instead of 0, if I were to plug in 0 for x, the cosine of 0 would be 1, so my new bound is actually 1. My lower bound is 1 now. And then my upper bound was pi over 2, but again, if I plug that in for x, cosine of pi over 2 is 0, so that means I'm going to 0. Now that's a little bit odd if you're going from 1 to 0. We're not usually ordering those in that way. You want to go from low to high. So you can fix that by simply, in this case, pulling a negative out in front, and that switches the bounds. So I'm going to make a negative out in front and then go from 0 to 1. And then anywhere I see a cosine, I'm just going to replace it with the letter u. So this is now really just u to the 9th for this first term that was cosine to the 9th of x. And then after that, in parentheses, remember we had 1 minus cosine squared of x squared. Well, if you expand that, which I'm not going to show completely here, but if you just do the algebra to expand all that, that is square 1 minus cosine squared of x, which of course would be 1 minus u squared, then you'd end up algebraically with 1 minus 2u squared plus u to the 4th. And if you want to just kind of write that out in detail to double check that to make sure it's clear, that's probably a good idea. And then sine x dx, of course, that gets replaced with du, but then this extra negative sign that we had, which we had to bring out, it just became part of the substitution step for the derivative of cosine, right? Well, that negative is going to combine with the extra negative that we have out in front to eliminate it, which means ultimately we can rewrite our next step. Actually, hold on, let me put my du here. And we're going to say this equals the integral from 0 to 1 of u to the 9th. If you distribute the u to the 9th in all these terms, of course, that's just some basic algebra. You should end up with u to the 9th minus 2u to the 11th plus u to the 13th du. You can double check me on that. I think the algebra is there. I'm just not showing every little detail of it. And then, of course, this is just fundamental theorem of calculus, which you can do, right? Antiderivative of all these terms, add 1 to the power, divide by that new power, evaluate from 0 to 1. You should end up with the value of 1 over 210. And again, I'm not showing every little detail just for the sake of time and space, but you can work through those, hopefully with some familiar knowledge of Calculus 1, and find that that is the case. Our second example begins as follows. The integral from 0 to pi over 2 of cosine squared theta d theta. Now, to approach this one or begin it, we're going to recall what we have above. So directly above in our notes, you can recall the power reducing formulas. And for cosine squared, we would get the following. So we could say that, as we said above, cosine squared of, in this case it's theta. You could use a different variable, I suppose, but this problem is using theta, so we'll say it in that way. So cosine squared theta, as we said above, would be equal to 1/2 times the quantity in parentheses 1 plus cosine of 2 theta. Again, that's just directly from above, related to the half-angle identity in trigonometry, but that's what we can use in this case because we're staring directly in the face of, well, cosine squared theta. And there is no other method that will work to integrate this. You could try anything you know already. Cosine squared theta is not going to go anywhere useful. So what we're going to do is rewrite this integral in the following way. So we're still going from 0 to pi over 2. We're not doing a substitution here where we would have to change the bounds of any sort. We're simply replacing cosine squared theta with its equivalent given that identity we just referred to. So we have, instead of cosine squared theta, I'm going to write the integrand as 1/2 times, in parentheses, 1 plus cosine of 2 theta. And then, of course, we still have this d theta. But this enables us to use more basic integration methods. So algebraically, what we're looking at, which I'll rewrite, is simply the integral from 0 to pi over 2 of the 1/2 could be distributed into the parentheses of this integrand, which would give us, of course, 1/2 plus 1/2 cosine of 2 theta. And you could think of that as just two distinct terms in this integrand. I'll put those in brackets just to make sure it's clear that the integral is still applying to both terms. And then, of course, we still have our d theta. But since we know term-by-term integration, where you can take the integral of each term on its own, we could then just split this into two separate integrals from 0 to pi over 2 of 1/2 d theta, the first term, and then plus the integral from 0 to pi over 2 of, now the 1/2 cosine 2 theta could be such that I put the 1/2 constant out in front. So I really have 1/2 times the integral from 0 to pi over 2 of cosine of 2 theta. And thankfully, again, this breaks it down into more basic integration that we can do with just our memorized antiderivatives here. So let's continue on to finish this one up. In our first term, of course, the antiderivative of 1/2 d theta, of course, would just be 1/2 theta. So we're going to write this as 1/2 theta, but of course we're going to evaluate that from 0 to pi over 2 using the bounds that we have. Do that shortly. And then plus our second term was the 1/2 constant in front. I'll keep that in front as well, but now we want the antiderivative of cosine of 2 theta. Well, think about this a little bit. The antiderivative of cosine is sine, so we know it's going to be just a sine, but then if you were to think backwards here, if I had sine of 2 theta, if I just kept the input as 2 theta, and if I took the derivative of it with relation to theta, so d theta of sine 2 theta would be cosine of 2 theta, but then the chain rule would mean I'd multiply by the derivative of that inside argument, which would be just a 2. So we have to account for this extra constant that would happen using, this is just kind of our thoughts off to the side here, using derivative chain rule, which means the antiderivative of cosine of 2 theta would be 1/2 sine 2 theta. And of course, this is going from the same bounds 0 to pi over 2. So this extra 1/2, I'm going to put this here highlighted so we remember. This extra 1/2 that popped out with the antiderivative is because we have to account for this constant that, if going forward with a derivative, would pop out. We want to cancel that out going in an antiderivative direction. Okay, so, and that means, of course, that if I were to take the derivative of 1/2 sine of 2 theta, that 1/2 would stay there in the derivative and therefore cancel with that constant of 2 that would be popping out with it, giving us only the cosine 2 theta that we're supposed to have in this integrand. All right, so the rest is now just kind of crunching this out with the bounds as given. And with a 0 as a lower bound, of course, that makes our lives easy because you're subtracting, just plugging in 0. It's a simple substitution. But let's write out what I think we should get for this, which would be there's a 1/2 constant. You could factor out of the whole thing. Notice there's a common 1/2 for both of these terms. So we'll just kind of pull that 1/2 out in front. And then in some brackets, we'd be left with, let's see, it looks like pi over 2 plus 0. Or you could say minus 0. Same difference here, but you're evaluating that first term at those bounds from 0 to pi over 2, just using the fundamental theorem here. So f of the upper bound minus f of the lower bound. And then secondly, you'd be subtracting the second term, which all just turns into zeros. If you plug in pi over 2 for theta, of course it's 2 theta, which means 2 times pi over 2 is just pi. Sine there is 0, and of course plugging in 0, sine of 0 is also 0. So you're evaluating this, getting just zeros for the second portion of this, which means altogether, if you simplify the arithmetic, I believe we'll end up with pi over 4 as our final result. All right, our third example begins as follows. We have the integral from 0 to pi over 2 of sine squared x cosine squared x dx. Now, I'd like to acknowledge a couple different paths that we could take on this one, and we'll end up just kind of picking one of them. But there are some options, as is the case in many math problems. So in this one, you're looking at what you could see as part of our power-reducing identity that we have listed above. Like, so sine squared x can be replaced with what we have above in our notes for the power-reducing formula for sine squared x. Or same thing with cosine squared, that is the next factor in this integrand. And you could end up just multiplying those equivalents together. That's one option. Another option that you could also approach here is to force or kind of manipulate this integrand to match up with another identity that we also recalled above, and that is the double angle identity. So, for example, I'm going to just kind of write some of these notes off the side. So recall a couple options here, right? So the double angle identity is what I mean when I say sine of 2x is equal to 2 sine x cosine x. Or again, you could be using theta for that instead of x. But we recalled that identity above, and you have used it before just from trigonometry. Sine of 2x equals 2 sine x cosine x. That's a possibility to use here. Why? Because what we're looking at is not exactly 2 sine x cosine x, but it's not terribly far off. And with a little bit of algebraic manipulation, we could actually make it work. I'll explain that in a second. But let's also recall that we know these power-reducing formulas from above, and we've used some of those recently, and I'll kind of write them down here as well, just so we have them fresh with us. We said above that sine squared x is equal to 1/2 times the quantity in parentheses 1 minus cosine of 2x. Or, similarly, we know that cosine squared of x is equal to 1/2 times the quantity 1 plus cosine of 2x. So these are things we've been kind of listing or recalling here, and they're relevant to this problem. I want to write them all down so we can discuss how to use either one. So I said there are a couple options, and I want to just kind of briefly explain just for the sake of experience. You could kind of pick one or the other, whatever one just kind of seems more usable or user-friendly too. If we were going to use this first identity, the double angle for sine, the first one I recalled here, then notice, of course, our integrand doesn't match it exactly, but it would be an option to rewrite this integral. I'm going to do this just to demonstrate. We could rewrite it from 0 to pi over 2, as given with the bounds. And then since we don't actually have this factor of 2 that is in the double angle identity for sine, notice we're missing it in this integrand. And of course, these are signs that are squared, and that matters too. But you could actually do a little bit of manipulation to, it almost feels like you're forcing it here, but it is an option. You could rewrite this as 1/4 times 4 sine squared x cosine squared x. Now, why do all this? Well, because what that does is allow us to kind of force this identity in here, where we now, instead of having 2 sine x cosine x as the identity states, we have 4, but that's still usable in this way. Because we could rewrite this integrand as the integral from 0 to pi over 2 of, we'll keep the 1/4. In fact, I'll put the 1/4 constant just out even in front of the integral to the left of it. And then what we had in parentheses in this previous step, which was 4 sine squared x cosine squared x. Again, it doesn't match the double angle identity exactly unless we do one quick little algebraic manipulation. I'm going to rewrite that set of parentheses as 2 sine x cosine x all squared in the parentheses, which would be algebraically equivalent, right? You'd be squaring the 2 to get the 4, squaring the sine to get the sine squared, squaring the cosine to get the cosine squared. What that does is create a situation where you now have the double angle identity in place. So I could rewrite that as 1/4 the integral from 0 to pi over 2 of, now in the parentheses, which are squared, we really have the identity for sine of 2x. So it's really sine of 2x, or you could say sine squared of 2x dx. So that's a possibility, and then of course you can go further with that. Now, that's one way to get to the place there of sine squared of 2x, but it's not the only way. And so this way, if you thought of it or want to use it, if you see this kind of thing again, it will work. But I'm going to back up and also show another method or another option. Actually, you know what? I'm going to do this. I'm going to leave that all there, but I'm going to show the other option in a different color just so we can kind of keep them both present. So I'm going to say that's a possibility which you'd have to keep going with. Or another option would be to do the following. I'm going to take this original, so the integral from 0 to pi over 2 of sine squared x times cosine squared x dx. Again, that's just the original given integrand. But if I simply replace both of those factors with their power reducing formula equivalents that we've also recalled, then it's also possible to replace this integrand to be, well, notice each of them would have a 1/2 factor in front, but if you're multiplying those both together for sine squared times cosine squared, then you'd have a 1/2 times 1/2, which would become a 1/4 as a constant, which I will put out in front of the integral. And then I would have after that the 1 minus cosine of 2x times 1 plus cosine of 2x. Again, just multiplying those two results together for these power reducing formulas that we're recalling from above. And then of course dx at the end. So both of these options will get you where you want to be. Let's figure out how, because we're not quite there with this second option. If I were to continue on, which I'll do, you can write this as the integral from 0 to pi over 2 of, I'll put the 1/4 constant out in front still. And then notice here's just a little bit of algebra. 1 minus cosine 2x times 1 plus cosine 2x. That's just a difference of two squares, which happen. Remember, think of algebra. A plus b times a minus b is the same thing as a squared minus b squared. So that's the same thing as 1. That's like a squared or 1 squared. And then minus the second term squared, which would become cosine squared of 2x. That's just a difference of two squares algebraically on those two previous sets of parentheses. Or you could FOIL those together by multiplying them to get the same thing. So just some algebra there. Sine squared 2x dx. Okay, so either way that I've now illustrated, you can get to that place. But of course, you still would need to finish that. So we can now turn that into, if you went this way, you could replace that with another power reducing formula from above for sine squared. You could use that method. Or you could again continue the same thing I think above, where you replace in our first option sine squared of 2x with its equivalent power reducing formula. Either of those ways, meaning when you replace that, we should end up with the following. Sine squared, let me use a better color than that. So hold on. We're going to take this sine squared of 2x that we had in our previous step for the integrand. We're going to replace that using the double, the power reducing formula we have above that we recalled. But in doing so, we have to be a little bit careful as well because the inputs are different. So what we're now seeing as an input is 2x. We have sine squared of 2x. And our power reducing formula is a sine squared of x. So that means we're going to have to double the value on the other side. So instead of now this double or this reducing power reducing formula saying 1/2 times 1 minus cosine of 2x, since our input is already doubled, we're going to have to double that to make it a 4x. Okay, so let's put this all then together. We have now equal to 1/4, hold on, get my pen out here. So this is equal to 1/4 times the integral from 0 to power 2 of, it'd be 1/2 times 1 minus cosine of 4x. So there's that doubling of the angle, which let me highlight again here. The 4x is coming because you're doubling the input in the previous step, which means you're doubling the input in the formula from 2x to 4x. That is the power reducing formula. So here we are, 1/4 times the integral from 0 to power 2 of 1/2 times the quantity 1 minus cosine of 4x, and then dx. Now, this at this point is an antiderivative that resembles some things we did in the previous problem. So what I'm going to say is make it a little bit of an exercise to try to finish this one. So I'm gonna put the result. I believe you should get, try this. You should get pi over 16 for your final result. I'm going to just say here, try finishing. On your own, just as a little bit of a practice. Again, refer to the previous example for your antiderivative when you have an input of the trig function that has a factor in it, like we said earlier. So you can hopefully resemble or see the resemblance of this antiderivative. That is, when you get to the antiderivative of cosine of 4x, it's going to kind of resemble the antiderivative we did in the previous problem where we had sine of 2 theta and we had to have that extra constant of 2 that showed up. Which turned into actually a 1/2 when the antiderivative came out. So that kind of thing is going to happen similarly here because you have a constant this time, it's 4x. So you might expect to see some adjustment with that. But try finishing this one, see if you can get pi over 16. All right, our fourth example is the integral of the square root of cosine theta times, now after the square root, we have sine cubed theta d theta. Now, let's go back up to our notes. In fact, look back up there if you like, just to make sure you're familiar with our strategies for these sine and cosine integrals. Remember that one of the things we want to do is be able to break off an extra factor of sine or cosine. And in this case, since you see an odd power of sine, being the sine cubed theta, that's motivation to say, well, we could break one of those off and then still have a usable sine squared theta present. So we're going to try that method. I'm going to take this and rewrite the integral as the square root of cosine theta. We're just going to leave that alone for a second. But then instead of sine cubed theta, we're going to rewrite that as sine squared theta times sine theta d theta. All right, so let me put some underlining in here to help hopefully indicate here. We're taking that sine cubed theta and we're splitting it up to be sine squared times sine. Now, why are we motivated to do that? Well, let's now rewrite this again as the integral of the square root of cosine theta. But now I'm going to replace sine squared theta with its equivalent from the Pythagorean identity. We know that would be equal to 1 minus cosine squared theta. And let me just highlight this to make sure this is clear. So sine squared theta is now just 1 minus cosine squared theta. You may be wondering why we're doing that. Well, hold on. Let's see if we can figure that out. But I'm going to keep going then to finish this. We still have a sine theta and then d theta to finish. Okay, now why did we do that? Why did we replace the sine squared theta with 1 minus cosine squared theta? We know that they are equivalent from the Pythagorean identity, but what use does this have? If you have an integral that has some form of cosine, I'm just going to use cosine theta since that's our variable, but it doesn't really matter what the variable is. If you have some kind of cosine factor or portion of this integrand, and then after it, in a later factor of this integrand, you have a sine theta d theta, then you are ready to use a u substitution, because then you know that the derivative, if you let u equal cosine theta, then du is going to be sine theta d theta, which is also in your integrand, and you're good to go. Let's do a little bit more algebra to get this user friendly. I'm going to rewrite this as the integral of the square root of cosine theta times, if I were to distribute this square root of cosine theta to those factors after it in parentheses, it could be simpler, or it might actually be even easier to do the substitution first. So let's do that. I'm going to go back up and say, you know what? Right now is a good time to do the substitution. So let's do this. We'll pick on our favorite substitution variable, the letter u. We're going to let u equal cosine theta. And again, we're motivated because we have cosine theta as part of our integrand. And then watch this. If we now go through with the substitution by finding the derivative of u with respect to theta in this case, so du would equal, the derivative of cosine is negative sine theta, and then d theta if we're multiplying by d theta on both sides. And notice that's what we're talking about. The sine theta d theta is in our integrand already. So let me highlight this because we're happy about it. Sine theta d theta, of course, we have that extra negative constant to deal with. That's no problem. But sine theta d theta is part of our integrand, which is a good thing for our substitution. So we can now go back and rewrite this as, I'm going to replace all these cosines of theta with, well, just u. So let's do that next. Hopefully in the right color here. Okay, so we have equals the integral of, we had square root of cosine theta, but now that's going to be square root of u times, in fact, to skip ahead a little bit, let's call that u to the 1/2. Same thing, but it's more algebraically friendly for us. All right, u to the 1/2 is the square root of u, which is now replacing cosine, times in parentheses 1 minus u squared. Again, replacing cosine with u, so cosine squared is now u squared. And then we had sine theta d theta, which is now just going to be du. But remember, there was an extra constant, so we have to make sure and account for that. I'll just throw a negative sign out in front of the integrand to do that. Let's carry on another step here. If I continue on, we'll write this as the integral. I'll put a negative or keep the negative out in front. If I were to distribute this u to the 1/2 inside our parentheses, this is what I mean by more algebraically friendly about writing it as u to the 1/2 instead of the square root of u, because now you can use exponent rules. If I distribute that u to the 1/2 inside, I'll end up with u to the 1/2, that is itself times 1, and then minus. If I have u to the 1/2 times u to the second, remember you're adding those powers to multiply those factors together, which will give us then u to the 5/2. And of course, this is all du. We could be even a little bit more fancy to make this look better by distributing the negative sign that we have out in front into the integrand. If we did that, if that negative sign that was in front of the integrand gets distributed in, it will ultimately just switch the order of our two terms since they have a subtraction between them. So we're really looking at the integral of u to the 5/2 minus u to the 1/2 du. Okay, so just a little algebra there going on. Of course, now we get into just basic integration, fundamental theorem. This should turn out to be, let's see, 2/7 times u to the 7/2. This is antiderivative of the first term. And then minus, for the second term, it'd become 2/3 u to the 3/2. Again, just antiderivative there. Now, in this case, notice there's no definite integral. This is an indefinite integral, so there are no bounds to put in or to evaluate it at. So this is where we definitely will need the plus c. But we don't want to leave u in this problem because there was a substitution. So we'll go back and replace that to end up with 2/7 times cosine theta. Now we're just replacing u with cosine theta to the 7/2 minus 2/3 times, same replacement here, cosine theta, this time to the 3/2, and then plus c. We need our constant for this indefinite integral. Okay, and there's our result.
All right, our fifth example is sine squared x times sine of 2x dx. Now, notice we're dealing, in this case, initially all with sine functions. That's good to know. But also notice what's looking familiar as an identity here, the sine of 2x. Remember, any trig identity that we know could be used for you. So, in this case, what do we call that? And I'm going to rewrite this integral as the following. It's sine squared x as given, but then instead of
Sine of 2x, we're going to rewrite that as 2 sine x cosine x, because that's what it is. That's the identity of that type. So in fact, maybe I'll even highlight this just to make sure this is clear. So sine 2x is really 2 sine x cosine x. See trig identities. Okay, and then let's not forget our dx as well. Now, why do we care? Well, we're starting to see something that looks useful, and I'm gonna do one more step before we dig into that. So I'm gonna rewrite this again one more time as I'm gonna multiply a couple things together. First of all, notice that we have this extra factor of 2 that came out in that identity for sine of 2x. I'm gonna let that float to the front. Just for simplicity and style here. So that 2 is going to just be written out in front, no problem. But then notice we have sine squared x and sine x. If I multiply those together, then we have, well, sine cubed x. And then we also have this factor of cosine x dx. Now, why is this a good place to be? Can you think of it? Think back to the previous problem. What we're looking at is a situation where we have an integral. I'm going to do this off to the side in a bit different color. We have an integral that involves some kind of sine x function or combination. In this case, it's sine cubed x, okay, times cosine x dx, which is what our integrand has. This is actually a good place to be. Again, see the summary of sine and cosine integrals that you might see in a textbook. You'll usually see a summary box or kind of strategy tip where you want this situation. Why? Because now it's set up favorably for a substitution. So if we let this time u equal, and we want it to be the, in this case, sine x, the portion whose derivative is also in the integrand, right? The derivative of sine is cosine. That's a good motivation to let u equal sine x. It's kind of the reverse of the previous problem where we did a similar kind of thing. In that case, we were kind of using cosine instead, but it's a similar situation. And here we have a sine of x, in this case sine cubed of x, and then its derivative cosine x also in the problem. So if I let u equal sine x, then of course du, the derivative of sine is cosine x, of course dx is really du over dx, and you multiply on both sides, right, that whole thing. So it's du equals cosine x dx, which is in our integrand. So this is looking good for the substitution. Let me rewrite now everything. We have the 2 constant out front, integral of, it was sine cubed of x, but if u is sine of x, then we're literally looking at just u cubed, and then du is going to replace cosine x dx. So all of a sudden it's way better. This is now just 2 times the integral, well, let's just do the integral here. The antiderivative of u cubed would be u to the 4th over 4. And then if we're going to need a constant here because this is an indefinite integral, so we'll say plus c. And let's simplify this one quick step. We have 2 over 4. You can reduce that to be just 1 over 2. So we're looking at u to the 4th over 2 plus c. The problem is nobody cares about u, the letter u that is. So we want to replace that back with sine x as we said originally. This is now then 1/2 sine to the 4th x, or sine of x to the 4th power, typically denoted as sine to the 4th of x, and then plus c. All right, our 6th example is as follows. We have an indefinite integral of sine of 8x times cosine of 5x dx. All right, now for a problem like this, you can scramble around looking for identities that may or may not apply here, and there are some, so I want to refer to these, but I also want to say that these are not necessarily ones that are typically required by memorization, but you do need to be familiar enough to recognize them. So I'm going to just kind of point this out. Recall, I did not have this one listed above in those that do need to be memorized, but I do want you to be able to recognize this. So let's recall there's something called a product to sum identity. And for a case like this, the formula goes something like sine of a times cosine of b. And sometimes different variables are used. You could use alpha and beta, u and v. It doesn't really matter. But you have typically the definition given in this kind of way. I'm going to use capital A and capital B. So sine of capital A cosine of capital B is equal to, the formula or the identity says this, it's equal to 1/2 times, in brackets, what I'm going to put as sine of capital A plus capital B, and then plus sine of capital A minus capital B. All right, so let me make sure this is readable enough. We have sine of capital A times cosine B. I'm just going to call it A and B. There's no other lowercase floating around in this problem, so we'll just use simple A and B. Sine of A times cosine of B by this product to sum identity is as follows. 1/2 times the quantity, now in brackets, sine of A plus B plus sine of A minus B. And those A plus B and A minus B's are in parentheses, and then close the brackets. Okay, so that may not have been obvious, but I do want it to be recognizable, even if it's not something required to be memorized. It's good to be able to recognize and go, I think there's a lurking identity here, and then be able to search through your tools and figure that out. All right, so then if that's the case, we can rewrite this problem in a more user-friendly way instead of the way it was given. This is rather the integral of. Now there's an extra 1/2. There's a 1/2 factor in front for this identity. I'm going to put that just out in front of the integral. As we know, constants can float out there to just look a little bit better. And then we have in brackets, now in this integral, it's going to be the, let's see, sine of. Now, in this case, for the identity, it was a plus b. Well, a, as we've kind of designated this, a is like the 8x, and b is like the 5x in this problem. And so a plus b would be 8x plus 5x. I'll write that out in detail for now, just so it's clear. So we have sine of 8x plus 5x, and then we have plus, and then sine of a minus b would be 8x minus 5x. Those are each in parentheses. I will then close up some brackets and then put a dx after it. It's probably also worth noting that since we're adding these terms in this identity, it's the sine of a plus b plus the sine of a minus b. Since you're adding them, of course, that's commutative. You could switch the order of these terms and put the 8x minus 5x first. It doesn't make a difference in that case. But let's now continue to see if this makes it any better. I'm going to rewrite this as 1/2, that constant that's out front, times the integral of. If we just add like terms now within this identity formula here, we have 8x plus 5x. Well, that's just 13x. So we'll call this then sine of 13x plus, for the second term, it was 8x minus 5x. So of course we can combine like terms there and make that sine of 3x dx. If you want to put, brackets or parentheses around these terms, you can. We can understand them hopefully to be all within this integrand here. Now we're just looking to take this integral, which means just antiderivative. So I'm going to keep the 1/2 out in front. Now for sine of 13x, we're looking for that antiderivative. This is similar to some things we've done before. It should end up being an extra 1/13 constant times the antiderivative of sine would be negative cosine. So I'll make this negative cosine of 13x. Now, why is there the 1/13 there? Because remember, when you're taking the derivative of cosine, you would end up multiplying by the chain rule by an extra 13 for the derivative of 13x, which is why you have to cancel that out with the 1/13 since it wasn't in our previous steps. That's just antiderivative with the constant in the input as stated there. We've seen that before. So we have then this 1/2 kind of out front. In fact, let me put that in parentheses out front, the 1/2. And then we're doing antiderivatives one piece at a time. So we have this negative 1/13 is really what it will be because of the negative sign that's also present in the antiderivative there. Cosine of 13x. But moving on, for our next term, same kind of thing. It's going to be a minus 1/3 cosine of 3x. And close parentheses. Now we've done the antiderivatives, so we can put a plus c at the end. Maybe clean this up one more time by distributing the 1/2. So we should end up with, looks like, negative 1/26 cosine of 13x. And then minus 1/6 cosine of 3x, and then plus c. And again, that's assuming we've distributed this 1/2 factor to both terms, and that should be our final result. All right, our next example, number 7, is the indefinite integral of a fraction whose numerator is sine squared of 1/t, and whose denominator under that is t squared, and this is all dt. All right, so again, you may be kind of sifting around in your toolbox of what to use here. This one is, as you may be able to recognize, set up fairly well for a substitution. Now, there is a sine squared here, which we're going to have to deal with eventually, but we do have an identity for that above. Until we get there, though, notice before then, even a need or a use for a use substitution. I'm going to let, or just a Triggs, an substitutionary integral here. I'm going to let u equal. We want it to be something whose derivative is in the integrand as well. You may recognize 1 over t as a good candidate for that. So if u equals 1 over t, of course, that's the input of our numerator trig function. So that would mean then du equals the derivative of 1 over t. Of course, that's also t to the negative 1, would be negative 1 over t squared. And then dt, of course, this is happily part of our integrand. We have a 1 over t squared. Now, of course, there's a negative constant. No problem. We can fix that. That's extra in our substitution. But let's now use this to go back and rewrite our integral with the substitution so that we end up with the following. It's the integral of sine squared of u now, since u is really 1 over t. And then 1 over t squared dt gets replaced, but there's an extra constant we have to throw in there as well. So I'm going to put that constant out just in front of the integrand, the negative, that is, and then du will replace the rest of that. So we now have the integral, negative, the integral of sine squared u du. Okay, that's fine, but we're still not in a convenient place for an antiderivative unless we use another identity for sine squared. So let's do that. Now I'm going to keep the negative out in front of our integrand, and I'm going to replace sine squared u with our power reducing formula from above. So double check by going back to look at that. That should be the 1/2 times, in parentheses, 1 minus cosine of 2u. We're doing this now, the rest of this, using the substitution variable where u is replacing 1 over t. So now we're kind of in the land of u here, doing this power reducing formula. And so we also then put du after it, since that's where we are. All we've done so far here is replace. We have this sine squared of u gets replaced with its power reducing equivalent, 1/2 times the quantity 1 minus cosine of 2u. Now, of course, we can do a little bit more with this. So moving on, this is going to be 1/2. If you distribute the 1/2 to both of the terms after it, it's really 1/2. Well, let me do this a couple steps. So I'm going to keep the integral out there. In fact, the negative in front of it even. We have then is the integrand. If I distribute the 1/2, it's 1/2 minus 1/2 cosine of 2u, and then this is all du. So we'll just do some antiderivatives here. All right, let me jump in with our antiderivatives. So I'm going to skip a couple details. Definitely work through them carefully, especially if you feel like you're tripping over them. But if you take the antiderivative of where we were in our previous step, we should end up with negative 1/2 as a factor out in front of, and then in parentheses I'll put u minus 1/2 sine of 2u, and then close parentheses, and then plus c. Don't forget our constant here with this indefinite integral. That's the antiderivative with using u. Of course, then you'll have to replace u being 1 over t, which should give us a result of negative 1 over 2t plus 1/4 sine of 2 over t plus c. Now again, I haven't shown maybe every detail of going from one step to the next. I want to leave that. That's just some more fundamental kind of antiderivative work. Work on that and make sure you can match it up with these results. That should do it. Okay, last example of this topic. I know it's been a lengthy one here, but let's see. Number 8 is the following. We want the integral of t times sine squared t dt. Now, as you look at this thing, you'll notice immediately some trigonometry involved, specifically a sine squared t. And you may, I think, rightfully think to use a power reducing formula for that. So I'm going to keep the constant, or not the constant, the simple degree 1 factor of t just in front of this integrand here. So we have the integral of t, but then instead of sine squared t, let's go ahead and use the power reducing formula we have above for it, which is 1/2 times parentheses 1 minus cosine of 2t, close parentheses. And so that is now what we can use for our integral, of course, dt. We want to clean this up a little bit, and I think it'll turn into some fairly basic work for the finishing steps of it. So let's continue. This is then the integral of, if you have t times this 1/2, you could leave that as, let's see, I'm going to put the 1/2 factor out in front of the integral. It's just sometimes nice to put those constant factors out in front. So we're really working with 1/2 times the integral of, if you then distribute the t to both terms that were in parentheses, that is in the 1 minus cosine 2t parentheses, if you distribute the t there, we're looking at the integral after the 1/2 of t minus t times the cosine of 2t dt. And if you want to put that all in brackets to keep clear what is the integrand, that's fine. Now, from here, we're going to have to be very careful about this because, first of all, I think it's going to be more clear if we split up some of these terms just to distribute and make it look a little bit simpler. What I mean is I'm going to rewrite this as 1/2 times the integral of t dt. I'm just kind of splitting up the terms. There's the first term, and then the second term will be similar, so minus, and then we'll have 1/2 times the integral of t cosine of 2t dt. All right, so all we're doing at this point is splitting up the integrand pieces so that it's like you're distributing the 1/2 integral, and the result, of course, will end up with what looks like two terms. So that's just some algebraic work. Why would we do that? Because then the first integral is actually fairly simple. 1/2 times the integral of t dt, no problem, right? It's the second one that gets a little trickier. So let's kind of break this down one piece at a time. If I take that first integral, 1/2 times the integral of t dt, of course that's just going to be t squared over 2 as the antiderivative of t, and then of course there's a 1/2 that was in front of it, so we'll have to keep that with it. Now, if you look at the second integral, this is where it gets a little interesting. Nothing simple will work here, meaning even just like a substitution, like a u sub, won't do it. If you let u equal 2t, then du equals 2 dt. It does not account for this extra t factor we have in the front of this integrand. So we have to break out a method we've used recently called parts. So we're going to say use parts. And by that I mean integration by parts. To do that, we're going to have to identify all the key pieces, right? So you have u and dv. So in this case, going back to what we've used for that, if you can review the integration by parts, tips and strategies, it would make sense to let u equal t in this case, and dv to be the rest, which would be, of course, cosine of 2t dt. You have to account for everything, and I think we have, but in ways that are strategic for the integration by parts method, which would mean then that du equals dt. We've seen this kind of stuff before. And then v would be, if you do the antiderivative of what dv was equal to, then v should be 1/2 sine of 2t. Okay, so that's the parts equipment that we will need for it. To do the actual work, then, we have to put it all back in the formula. So let's see, carefully here. I'm going to note that, remember to be careful with all your negative signs and such. So this minus sign that is originally, or in this previous step, rather, between those integrals, we're going to keep that minus sign there as is. And then after it, we have the 1/2 times this integral for which we're using integration by parts. I'm going to put the result of that in brackets. So the formula for parts is uv, so that would be 1/2 times t. We're multiplying u times v from our little parts work that we've done off to the side. So that would be, in this case, t times 1/2, so 1/2 t sine of 2t, just multiplying those values together. So there's uv minus the integral of v du. Well, that would be then 1/2 sine of 2t, there's the v part, and then du, which is just dt. Okay, so let's keep this all in mind. Now I've closed the brackets. These brackets are containing everything we just did by parts for this second integral in our previous step. All right, so there's a lot here to simplify, but that's all we have left to do. So if we rewrite this all, I think we'll end up with something of the following form. T squared over 4 for the first term, that's easy, right? And then minus, if we go through with this next part, I believe we should end up with a 1/4 t times the sine of 2t. And that is, of course, mainly just this second term here. And then lastly, so now we're going to have to do another antiderivative to get this last integral taken care of. But I believe that should end us up with minus 1/8 cosine of 2t. And then, of course, we need a plus c because this is an indefinite integral. All right, so check the details on this. The antiderivative of sine of 2t is what's showing up here. You can kind of work slowly through that as you need to and review what that is. Of course, the antiderivative of sine would be negative cosine. So check your signs, your SIGN signs on all these terms to make sure it's matching. I believe this is what it should end up being.